Hi everyone. We're at the last kind of topic of this unit, which is we're going to do um, discrete. So we talked about discrete signals, discrete all that stuff. Now we're going to talk about discrete complex exponentials. Okay, so this video might be one part, two part, depending on how long it takes, but this is kind of the important part of the unit. This is what is going to be used moving forward, discrete complex exponentials. So uh, before we start, please just remember this identity that e to the jx. By the way, I'm going to start using j instead of I for the complex number I. So j is the square root of -1. This is just like convention because we have I as electrical engineers. We use I for other things like current or whatnot. So e to the jx equals cosine of x plus j times sine of x. This is going to be very important to remember. By the way, I don't like using j, so I'm very used to writing I, so I might accidentally write I somewhere in between, but just know I and j are the same thing. Okay, so what is a complex exponential? They have two, so a complex exponential has two things, just like a discrete cosine had a k and an n. We use those to define a discrete complex exponential as e kn equals 1 over square root of n times e to the j 2 pi kn divided by n. Okay, so uh, this kind of again seems like numbers, but if you look, this 2 pi kn over n thing looks like really close to what was in our cosines and our sines. And if we use this Euler's identities, Euler's formula here to expand this, we see that this is exactly equal to let me do it in pink, equal to 1 over root n times cosine of 2 pi kn over n plus j sine of 2 pi kn over n. Okay, so the whole idea with this complex exponential is we've now represented the cosine, discrete cosine as the real part, right? And the discrete sine as the imaginary part. So in one complex exponential, we're capturing cosine waveforms and sine waveforms. And that was like what I said in the video, where it's like as this complex exponential spins around in the circle, right? Because e to the I theta is like spinning, changing theta means spinning around in the circle. Well, if you look from this way, you get a sine waveform, and if you look from this way, you get a cosine waveform, right? And so check out the other video if that doesn't make any sense. But what we've done is we've taken our cosine and our sine, and we've put it all into one exponential, complex exponential. This 1 over root n is very unimportant. It's called a normalizing factor. It just makes it so that some of the math works out nicely because we'll end up multiplying things and the ends will work out nicely. But for the most part, the important thing is the actual exponential itself. Okay, this allows us to do a few things. The big motivation is that it will make our analysis a lot easier. So imagine, right, if you had cosine, you had some cosine wave and you wanted to add an angle alpha to it, right? If you were to do this standardly with the standard way with just cosines, you would need to use whatever formula, right? Cosine of a plus b is cosine a, cosine of b minus sine a, sine b, something like this, right? Like you'd have to do that trig stuff and it gets really messy. But with a complex number, right, when you represent your cosines and sines as complex numbers, well, e to the omega t plus alpha is the same as just e to the omega t, so your original. Then you want to add alpha to it. Okay, that's multiplying by e to the alpha. And so addition of phase or angle, changing the angle, just becomes a simple multiplication if we deal with these exponentials. And so it makes our analysis a lot easier, and you will probably see that when we do some problems. Okay, so three properties of complex exponentials. The first property is that if k equals 0, then think about what this means. Remember, k again is the same thing. It's still a discrete frequency. So a discrete frequency of 0 means no oscillations. So e to the kn should look like a constant, right? And if we take e to the kn, by the way, e to the ekn is always a function of little n. So because that's what we plug into here. Everything else is fixed. This k, this n is fixed, but little n is what our input into the function is, or into the signal is. So if k equals 0, then e kn is what? 1 over root n e to the, this whole thing becomes 0, right? Because k becomes 0, so e to the 0, which equals 1 over root n. Okay, so this is a constant. So when we have 0k, then we get a constant, which makes sense. Okay, property 2 is that if k equals n, then we should also get a constant, and you can do that by plugging in. So let's plug in e instead of k, right? E to the kn of n. If k is equal to n, we go up here and we put in big N here. So we get 1 over root n e to the j 2 pi big N little n over big N, and these cancel out. Okay, here's something important. So what are we left with? 1 over root n e to the j 2 pi n. So how do we simplify this kind of thing? Well, we first write it as 1 over root n e to the j 2 pi all to the power of n. And maybe you can see this, maybe you can't. This drawing should show it. What does e to the j 2 pi equal? Well, we're going to use the fact that we know e to the j theta is cosine theta plus j sine theta. So then e to the j 2 pi is cosine of 2 pi plus j sine 2 pi. Sine of 2 pi is 0, cosine of 2 pi is 1, so e to the j 2 pi equals 1. Okay, visually, right, on the circle, this looks like, don't even know what that was. That looks like going a full 2 pi. So this is pi over 2, this is pi degrees, this is 3 pi over 2, this is 2 pi degrees. We end up here, and we see that this point is exactly the point 1, right? It's 1 plus 0i. So that's why we get 1. Okay, so this whole inside is equal to 1. So this becomes 1 over root n times 1 to the n, which is just 1 over root n. Okay, so if k equals big N, we're saying our discrete frequency is exactly the same as the number of samples we're taking. Then we also are left with a constant function. Okay, and this should make you realize that maybe if I have it working for some k and I add n to that k, then it looks like the outputs are the same. And that's something that we'll prove in a little bit. But lastly, the third property is that if k equals n over 2, okay, if k equals n over 2, then e to the k, ekn, I mix up how I say it, doesn't matter. Ekn of n is 1 over root n, e to the j 2 pi, instead of k we sub in n over 2, so big N over 2, so that becomes like that. This is some algebra stuff, whatever. These cancel, and we get e, I'm going to write it like this. We get, the 2's also cancel, right? So we get 1 over, I can scroll down, I forgot I can do that. 1 over square root of n times e to the j pi to the n. Okay, which becomes 1 over square root of n. And similarly, e to the j pi, you can think of going rotating pi degrees, so that's negative 1 times negative 1 to the n. And this is exactly, remember, k equals n over 2 is the frequency where we're oscillating the most, right? Because we have a certain amount of samples and we're going up and down at each sample. So that makes sense, right? That when n equals 0, we're at a positive. When n equals 1, we go directly down to the negative, positive, negative. So this is why, that's that alternating term. So when, for these three values, okay, my signal is entirely real. So you see that, right? My signal has no imaginary part. So whatever this imaginary part of the, complex exponential was, that, doesn't have any effect anymore with these signals, okay? Okay, so that's that. Let's talk about one property, which is that if I have, actually, okay, maybe we'll talk about that later. Let's talk about this property, which is that if I have, so given two frequencies K and L if they have the property if K minus L is n. So if L and K are n apart from each other, then I say I'm going to claim that e to the kn is ekn is the same as eln. Okay, so I have two frequencies K and L. I'm saying they're n apart from each other. So that's like kind of what these frequencies are, right? These are n apart from each other, and it looks like their outputs are the same. We can quickly prove that, right? We can say that, okay, what would ekn be? Well, that's e to the j 2 pi kn over n. Okay, but we're saying that k minus L equals n, so I can sub k equals n plus L into here. So I get e to the j 2 pi. I'm going to move the little n forward, then do n plus L over n. And this becomes, if we expand this out, e to the j 2 pi. Let me erase this real quick. It's coming away. Okay. This becomes e to the j 2 pi n plus j 2 pi n L over n. And again, this is what I'm saying is that, like, with exponentials, there's a property here that says, right, e to the a plus b is exactly e to the a times e to the b. So this naturally allows us to separate this into e to the j 2 pi n times e to the j 2 pi. I'm going to rewrite nl as ln over n. So you can immediately see that this guy right here is just eln, right? And then we have to show that we want to show that ekn is the same as eln. So maybe this thing should be 1, and you can see that it will be 1, right? Because this is going to be e to the j 2 pi to the power of n, which is 1 to the power of n. All right, so this will always be 1, and so we've shown this property. Okay, so a follow-up from this property is that, by the way, we put n here, but I could have put any multiple of n. So the idea is that if you have some frequency k, so if I have a frequency k and a frequency k plus n and k plus 2n, etc., these are all the same. So ekn is the same as ek plus n, which is the same as ek plus 2n, n, and that's what we just showed up here, right? If they're a distance L apart or alpha n apart, you can see this alpha would just come everywhere, and it would come into here, and that wouldn't be an issue. But if they're alpha n apart, then their complex exponentials are the same, okay? So what this means is that every n, we repeat the frequencies, right? So going from zero, right, k equals 0, then k equals 1, all the way up to k equals n minus 1, we've hit our n frequencies. The next k, which is n, is going to restart the cycle. So these two are going to be the same. And then similarly, you can see the pattern. K equals n plus 1 is going to be the same as k equals 1. Okay, so what this means is we really only need to keep n frequencies. So if we're sampling 32 times, we only need to keep 32 different values of k, because after that, everything's going to repeat itself. Okay, let's just wrap this up. So one example is taking 0 through n minus 1, right? So I could take 0, 1, up until n minus 1. A more common example that we do is we like to center them at 0. So you say, okay, what if my frequencies are centered at 0? Then I'm going to take 1, 2, all the way up to n over 2. And I'm going to take -1, -2, going all the way down to minus n over 2 plus 1. So this keeps a total of n. If you count this out, this is n things. So we keep our n frequencies. And the idea is that because we have n of them, we can choose whichever set that we want. So we could choose this set, we could choose this set. For analysis, we tend to choose this set. Okay, so I'll wrap this up, and then we'll finish in the last video with one more video.